operation where we reduce our cut depth to a very small amount, so 2mm, but we're going to run pretty high feed rate, so we're going to bump our feed rate up to like 6,000 millimeters a minute, so that's 6 meters a minute. In engineering, the way your feed rates are calculated is if you imagine your cutter is spinning, the circumference of your cutter is used to work out what's called surface speed. Now your surface speed is how fast the tip of your cutter is moving past the edge of your workpiece, and that's a really simple calculation. All we have to do is we pull up our little calculator. We have a 12mm cutter, so we're going to go 12 times pi, which gives us 37.8. Now the cutter manufacturer recommends that we spin our cutter at 300 meters a minute surface speed. So we're going to go 300 millimeters, but we need to turn that into meters. So chuck an extra 3 zeros divided by our value of pi, which is 38. And so it's recommending that I spin that at around 7,894. The cutter recommendations are just that, they're a recommendation. We're using a pure billet aluminium, which is obviously impurity free and is not very abrasive on cutters, so that's why we've bumped our speed rates, and this is where experience comes in. I know that the cutters that we use work best at 12,000 RPM for the 12mm solid carbide cutters, and the feed rates or chip loading, which is your X and Y feed rate, is usually about 0.1 to 0.2 per tooth, depending on your cut application. But again, depending on how much of a cut you make, it depends on how fast you can feed it through the material. Naturally, if you've got the cutter buried very deep in the material and you try to push it through, it's going to make a big old mess. So we're going to go 12,000 times 0.2. So we've got a 2-flute cutter, so that's working on a 0.1 per tooth feed rate, and that gives us a feed rate of 2,400. Now that would be the ideal feed rate if we were doing, let's say, a 12mm depth of cut, but we're not, we're doing 2, so we're going to ramp that right up. That's why we're at 6,000 millimeters a minute for this operation. But as I say, this is only suitable for doing a light cut. If we were doing a heavy cut, we would significantly reduce that. So we've got our cut set. We don't want to offset our tool radius. Our offset side of the cutter is the left. We have some options here to dictate how the cutter is introduced into the job. So our lead-in distance, so that's how far away the cutter will start from the job. So in this case we've got it at 20mm, which is nice to say. We have end overcut, which is used, if you imagine, if we make the cutter travel around that path where you start and finish your cut, you'll quite often be left with a little peak, which is caused from cutter deflection and spindle bearing deflection and material deflection. So what we do is we overcut, so we'll run past the start and finish, so we get an overlap. In this case we run 5% of that cutter overlap to eliminate that little peak, so that we get a completely perfectly blended surface. For our roughing and finishing, we're going to leave 0.5 of a millimeter on the walls for our finishing, and for our finishing we're going to do a incremental depth, because now naturally we're only taking half a millimeter off. We're going to put our incremental depth to 12mm. We'll leave our RPM the same, but we're going to significantly reduce our feed rate, so we're going to take that down to 3,000, because we need to get a good accuracy and also good surface finish. So that's all good. We're going to click OK, and you can see now these are all red lines. Those red lines are our toolpaths. So if I hit the simulate button now, it's going to face it off, speed it up a bit, and then it's going to start cutting out our profile. And you see, so this is the roughing process. It's doing 2mm depth of cuts, and then when it finishes, it's going to come up to the top and do our finishing. So there you can see we've faced it down and we've done our outside profile. So we've got most of it done. Now what we need to do, we need to quickly pocket that little hole out. It's exactly the same process as we have already used. except for our total depth for that pocket is only 1mm, so we're only going to select that. We have to change our entry mode for that because the pocket's so small, so we're going to change to an over and down and then up and over, so we're not going to have any overcut issues. And we don't need to run a finishing cut on that because it is simply a clearance pocket. Set our stock at 0 and click OK. So then what we can do is we can just click that and you see it cuts out our little pocket. That's great. Finally we have to do some drilling, so we're going to select the 2 holes and we're going to grab our 16mm spot drill. I'm going to spin at 6000 RPM, a feed rate of 500mm a minute. I'm going to use what's called a chamfer diameter, so that's how deep it's going to go to chamfer. In this case our drill and our spot drill is the same diameter, so it's not going to work, but we'll just put it in there anyway. And our clearance options, just like that, and then it puts some spot drills in. So if I go hit that, you can see it's going to come along and put some nice couple of little spot drills in. We'll do it for our centre hole as well, except we're going to change it to 12 this time, and we go OK. Oops. Let me just check that, that's great as well. Finally we grab our drill bit, which then drills our holes. Now obviously on this last one we also have to run a reamer down it. So when we come in here we select our reamer, we're going to slow the reamer right down. You can see it automatically updates due to the tool geometry. The feed rate's wrong, so we'll just change that. And we have to change what it's called, so it's going to be a boring operation and it's not a can cycle. And we go like that. Now it has got an error for some reason. Because the reamer was set on inch mode, so I had a 12-inch reamer as opposed to a 12mm reamer, but that is now correct. So we can go through and simulate the entire process of machining this now. And there you go. Now that little orange colour is just letting me know that the reamer has done its job. You can select different tool colours to suit whatever you're doing, so we could go through here and change our 16mm drill bit to a different colour. We can make it green if we want, just so that you can get a visual between different tools and where they're cutting. You see now the walls of the rotor or the 15mm holes are green, and there you go. So that there is literally exactly what the machine is going to do when it goes to manufacture the part. The first operation it's going to do, it's going to bring down a long series 12, it's face itself 2mm depth of cuts, and it's going to contour round, and then it's going to do 12mm depth of cut finishing passes on there. It's going to pocket out our hole, do some spot drilling, some drilling, and that is the part. It is that simple. What's really great about it all is if I select all our parts, it tells us what our cycle time is going to be. Now this is wrong. What this is telling me is our actual machine time. It's trying to tell me that it's 2 minutes and 4 seconds. That's not going to be right. There'll be some parameter in there that's not set up correctly, but with the correctly set up software it would tell you exactly how long it's going to take to machine. I know from experience it's going to take about 5 to 6 minutes to machine. So 5 to 6 minutes and 10 minutes if I wasn't doing the video to do a program, and you have a part. That's the beauty of modern machining and modern software to create parts in metal, more specifically for very simple parts. that's about all, and I hope this enlightens you a little bit as to how the manufacturing process or the programming process for CNC is done. Now what would normally happen here, actually, before I quickly go, is we have this function here where we click NC code and we use what's called a post processor. Now post processor is a intermediate processor which takes the information that this program spits out and turns it into a G code which is suitable for my machine to read. Every brand of CNC needs a slightly different language of G code or NC code to make it work, and that's where the post processor comes in. But when you've got a correctly set up post processor, I can hit my button here, it gives me my code, I send that to my mill and it's ready to go. I put my tools in, I put my part in, I set my zeros and I hit the big old green button and then it cuts out my part. Great fun. Anyway, hope you enjoyed that and cheers.